أيوة. السلام عليكم دكتور محمد جهاني موجود معنا. Are you with us?
وعليكم السلام دكتور علي.
Yes, Dr. Mohammed, how are you? I hope you are doing well.
Good, how are you?
Alhamdulillah. Yeah, I think you are with your colleague, Dr. I think Asma, you said, right? Dr. Mohammed, can you hear me?
A little bit, the sound is low. Can you please speak loudly a little bit?
So tired already. Long day. Almost 12-hour working. Alhamdulillah. Okay, so are you ready for conducting the session? I think the session time is already there, so maybe we can start the workshop.
Can I start now?
Yes, inshallah.
Can I share my, okay, let me share my screen.
Co-host, right? So Dr. Mohammed Ajani, first of all, I gave a short introduction about him and about his, he's a senior lecturer at the University of Tripoli. He is specialized in image processing, I think, FPGA design for embedded systems. Correct me, Dr. Mohammed, if I'm not mistaken, from the Department of Computer Engineering, College of Engineering, University of Tripoli. Dr. Mohammed is one of our scientific committee, as well from the review board of this conference. He worked a lot, very hard, as well as the other committees in reviewing and editing and guiding the scientific committee as well. Alhamdulillah, we achieved a very strong achievement for the first year of this conference. First of all, because of Allah. Second is because of this guy and the others. So I would like to thank you in front of the camera and in front of the all, and I wish you all the best in this insightful workshop. Go ahead, Dr. Mohammed.
Thank you, Dr. Ali.
Assalamu alaikum.
Alaikum salam. Welcome everyone for attending this workshop titled FPGA Design for Embedded Systems, Integrating Intelligent Computing with Hardware Acceleration. My name is Mohammed Ijhani from the Department of Computer Engineering, College of Engineering at University of Tripoli. So in this session, we will explore how FPGA are used to accelerate embedded systems and AI workloads. So you will learn about their architecture, design flow, applications, and how they provide speed, flexibility, and efficiency in modern intelligent systems. Here is the outline for our workshop today. First, we will discuss the architecture and functional advantages of FPGAs. Then, we will compare FPGAs with CPUs and GPUs. We will move on to the FPGA design flow and how to use hardware description languages. You will learn how to build, simulate, and deploy digital systems on FPGA platform. We will explore why FPGA are ideal for embedded AI applications. We'll look at real-world case studies and discuss some of our own research projects and publications. And finally, we will walk through hands-on session where CNN model is deployed on an FPGA using NICE2 software processor. So let's begin with the basic to see what is an FPGA. FPGA stands for Field Programmable Gate Array. It's an integrated circuit that can be configured by the user after manufacture. FPGA offer flexibility and can be reprogrammed to perform a wide variety of tasks. FPGA enabled parallel processing, which means they can execute many operations at the same time. This makes FPGA significantly faster than CPUs or GPUs for specific applications. So FPGA are powerful platform for building real-time embedded systems. Also, they are widely used in AI acceleration, offering a great balance of speed, efficiency, and adaptability. So let's see now why FPGA technology is important today. As we know, as a digital designers, digital systems become more complex. It's becoming difficult for designers to handle them using traditional logic design methods or traditional methods. The solution, FPGA offer a better solution. With FPGA, designers can describe digital systems behavior at different level of abstraction, can design in the data flow, structural, and behavioral level. The flexibility make development faster, more modular, and easier to test and simulate before committing to hardware or to the chip. So FPGA technology is essential for modern system design today because it simplifies complexity and enables high performance and real-time computing. So let's now take a closer look at FPGA architecture from inside. As we see here in this diagram, we can see what's FPGA inside. So at its core, FPGA is made up of large array of programmable logic blocks. These blocks are connected through programmable routing channels and also includes input from here, inputs and outputs interfaces to communicate with external devices. So what makes FPGA powerful is that the logic blocks and routing paths can be programmed by the designer to match any applications. So now let's have a look at hardware description language. That's the language that used to design FPGA. So to design with FPGA, we use something called hardware description languages. We have two kinds of hardware description languages. We have Verilog HDL, Verilog hardware description language, and we have the other language is called VHDL, which are used to describe structure and behavior of digital system, as we can see here in this code. It works at different level of abstraction, such as gate level, data flow level, and behavioral level. So one big advantage of HDL is that allows simulation, as we can see here. This means we can test and verify our design before loading it into the physical hardware on the chip. So before we load our design, we can test our code. If it's work, we can download it to the chip. So after the simulation, the HDL code is synthesized with the Quartz Prime software tools into actual hardware logic. So this code will be converted to hardware logic presenting this code. So this code, first of all, we simulate it, make sure and the result is right, and then we synthesizing to convert this code to the gate level output, which is streamed to the FPGA chip. Here we can see electronic design automation software tools provided by Intel Corporation. Intel provides a set of professional software tools to help with FPGA development. We have two software tools, as we can see here. The first software tool called ModelSim, used for simulation and debugging. So you can test your HDL code before hardware implementation by this software. The other software is called Quartz Prime. Quartz Prime is another software that handles several important steps, such as synthesis, place and route, and timing analysis. Here are the steps for design any FPGA design. So this chart shows the steps we can follow to design any FPGA system. So first of all, we start by writing our HDL code and test bench here, and then make function simulation using ModelSim here. And then we do synthesis mapping using Quartz Prime, that synthesis converting the code to the gate level file. And then we do place and route here. place and route for this code, and then go to timing analysis and simulation to simulate the time for the system, and then finally go to program the device. After that, test the integration in the board, and then release our design. So this steps we need to follow it to release any FPGA design. So as you see here, we use just two software, Model Sim and Quartz Prime software that provided by Intel Corporation. So now let's look at how do FPGA compare with CPUs and GPUs. So in the flexibility, FPGA fully configurable for different applications, while CPU is fixed in structure, in architecture, and limit by instruction set. GPU limited to GPU pipeline only. For execution model, FPGA's true parallelism has true parallelism via custom hardware logic, while CPU is sequential processing, and GPU use SIMD style parallelism, single instruction multi-data style parallelism. For the performance, we can see FPGA is faster and more efficient, especially in real-time processing, while CPU is low and GPU is high, but for complex tasks only. For the power consumption, FPGA has highly energy efficient, while CPU is moderate and GPU is high too. For real-time capabilities, which is very important, CPU is excellent for real-time processing embedded systems, while CPU is operating system dependent and GPU is very weak. For the throughput, FPGA has high for specialized pipelines, while CPU is from low to medium, and GPUs is high, but only for general purposes. Now let's see some FPGA research and development applications. As example, where FPGA is used today in the industry and in the academia. So in artificial intelligence, we have FPGA are used to accelerate machine learning and data processing tasks. Also, FPGA allow parallel execution, low latency, and energy efficiency, which is all essential for modern artificial intelligence systems. Intel Corporation integrated AI accelerators, Intel Xeon scalable processor, especially that help to run AI workloads at scale without specialized hardware. So this delivers powerful computing performance for entire AI pipeline, include built-in accelerators optimized for specific AI workloads across machine learning, data analytics, and deep learning. Here is the AI suite model development for FPGA, AI FPGA, sorry. So we have 3 steps. The first step is model, the second step is convert, and the third step is optimized for deploy. So let's see now in the first step, which is called pre-trained AI model. This block accepts model trained using any popular deep learning framework. Then in the second step, the model then optimize it using the OpenVINO model optimizer, which converts this converted files into intermediate representation or IR. This format is compact, efficient, and suitable for fast inference. So in the third steps, as we see here, we have 2 batches. The first batch is software-based inference, which is target traditional CPU. This batch go directly to traditional CPU, 8088 family or ARM RISC processors. The second batch, which is go to FPGA, the second batch is hardware based, not software. This is hardware based inference, where the IR model is deployed directly on FPGA using Intel AI suite and Quartus 2 software that we showed before in slides. So this how we deploy any program to the software or hardware design. We have another research development application, which is very important. The CNN, or convolutional neural network, is one of the most effective application of FPGA today, used by FPGA acceleration, is in convolutional neural network, or CNN. FPGA are widely used to speed up CNN-based tasks such as object detection and image segmentation, especially in real-time systems. So because CNN involved in many repetition mathematical operations, FPGA can parallelize those steps and complete them much faster than CPUs and GPUs. So now let's take a closer look at how FPGA compare with GPUs and CPUs, especially for AI now. So this table show or do comparison between FPGAs and GPUs and CPUs in AI. In the architecture feature, we can see FPGA offers customizable parallel data paths, while in GPUs have fixed massively parallel cores, and CPUs also are general purpose with few cores. For AI performance, FPGA has high efficiency and low latency tasks, customizable for CNN especially. And GPUs excellent for large-scale training, but not optimized for real-time. CPUs is poor for training and AI workloads. For power efficiency, as we can see, FPGA has low power per computation. GPU is moderate consumption, and CPU is low. For latency, which is very important, FPGA has ultra-low delay, ideal for real-time AI applications, while GPU is high due to memory bottlenecks and CPU's highest latency. Finally, in the flexibility, FPGA has full hardware level reconfigurability. We can reconfigure the FPGA many times, while in GPU is programmed via APIs, not hardware, and in CPU is software level flexibility. So another development application, research and development application, is digital signal processing, which is very important too. We have in this field, we have fast Fourier transformation. FPGA plays a major role in digital signal processing. So a great example is that fast Fourier transform, which is widely used in applications like audio processing and wireless communication. Then FPGA can implement highly parallelized FFT architecture, allowing them to process signal much faster than CPU and GPU. And we have a project we've done in this area. We will show later in slides. Another field is the telecommunications, which is very important. They use 5G networks. FPGA are widely used in the telecommunications today industry, especially with the rise of 5G networks. In telecom base stations and the network infrastructure, FPGA handle real-time signal processing tasks such as encoding and decoding of signals, modulation and demodulation, beamforming, and packet switching. So FPGA can process data streams in real time with minimal delay, and they can be updated or reconfigured to support the new telecom standards as they emerge. This makes FPGA an essential part of future-proof telecom infrastructure. Another important research and development application is cryptography and security. So in the field of cybersecurity, FPGA are used to accelerate cryptographic algorithms. FPGA are commonly used to implement AES and SHA and public key encryption, cryptographic systems. In network security also, FPGA also powerful firewall, intrusion detection systems, and secure authentication protocols. Another important research and development applications in video and image processing. FPGA can handle multiple image processing tasks simultaneously at the same time, such as real-time video enhancement, image filtering and edge detection, object tracking, and video comparison or decomparison. So this is useful in systems like medical imaging and automated inspection. Another field in research and development application is IoT. In IoT systems, as we know, large numbers of devices collect and process data in real time, often with limited power and processing capabilities. So here, FPGA are used in edge computing, where they handle tasks locally without needing to send all data to the cloud. This means faster decision-making, reduced bandwidth usage, improved privacy and security. Whether in smart cities, industrial sensors, or consumer wearable, FPGA help deliver intelligent processing right at the edge, that where it matters most today. So another field in the healthcare, FPGA are making a big impact in healthcare technology by enabling faster and more efficient medical systems. So for example, we have MRI and CT scanners. So FPGA used to help speed up image reconstruction, allowing doctors to get a result quicker. For ECG machines, FPGA enable real-time heart rate monitoring and advanced signal processing. In radiation therapy, where precision is critical, FPGA ensure accurate control and positioning in real-time systems. So let's now explore some our research projects we did over years. So I have some samples we go through to show what we did using this technology. First here, we introduce state-of-the-art real-world FPGA-based application titled Wake Up Board Speech Recognition. The system, this system is focused in extraction, specifically it extracts three key features. We have LBC and MFCC and enhanced MFCC at the same time. Simultaneously, the system extracts these features simultaneously. So we have LBC, linear predictive coding, and we have here MFCC, mil-frequency Kipster coefficient, and we have the third one is enhanced mil-frequency Kipster coefficient. Using an FPGA for this task allows parallel extraction, real-time response, and low power consumption. We have another project. In this project, we designed custom 16-bit RISC processor implemented on FPGA, as we see here. This processor supports a basic 8-instruction set, making it ideal for teaching computer architecture and for embedded control applications. By implementing this processor on an FPGA, students can visualize how instruction flow from model to model through this hardware and analyze performance of this processor, and then finally they can test different instruction architectures. Another project, this project takes the previous RISC, which is one stage, here processor further by implementing 5-stage pipeline processor. As we see this, we have 5 stages, 1, 2, 3, 4, 5 stages. So the benefit of this design, the processor is capable of executing 5 instructions simultaneously. Then this processor can execute 5 instructions at the same time, one in each pipeline stage. Implementing this FPGA helps students and researchers gain hands-on experience with instruction-level parallelism and real processor design. Another project is highly relevant to smart cities and showcases an intelligent density-based traffic system with Libyan vehicles license plate recognition on FPGA. So as we see here, the system is designed to manage traffic lights based on vehicle density in real time. It includes several smart features like red light violation detection, automatic license plate recognition, and dynamic light timing based on live traffic condition. Using FPGA allows the system to operate with high speed, low latency, and efficient resource usage. Another project in this project presents the design and implementation of smart rotary parking smart built on FPGA. The system includes rotating platform that can turn from side to side 36 degrees, allowing vehicles to be parked or retrieved automatically from any direction. The key benefit of using FPGA for this project include precise control over motor operation, efficient scheduling of parking slots, and real-time sensor feedback. By the way, all these projects done by my students in the Department of Computer Engineering, College of Engineering, University of Tripoli. Another project, this project demonstrates how to speed up fast-forward transformation operation using a custom instruction architecture built on FPGA. It uses the NICE2 soft-core processor combined with the custom hardware acceleration for F15. The goal was to reduce execution time in signal processing applications. Compared to the standard implementation in normal CPU, this design achieves up to 57% faster processing for 512.50 and over 50% improvement for large scale 5096 point transforms, as we see, I can see here in the table. Another project is in this project we designed an optimized implementation of AES encryption and decryption algorithm on FPGA. So to improve performance and security, our FPGA design includes a novel shuffle stage, which is a new algorithm. This enhancement increases data randomnesses and enables more parallel processing of encryption rounds. The result of this project is a system that offers improved encryption speed and high data security. This project focuses on real-time image enhancement using FPGA-based multitasking approach. The system can perform multiple operations like brightness adjustment, color inversion, image thresholding for binary output, grayscale conversion, edge sharpening, and contrast enhancement. All of these functions can run in parallel on FPGA, significantly improving processing efficiency. So let's now go over some publications we published in recent years in the area of FPGA. Starting, so over the year, our team or our students has published several research papers on FPGA-based systems. These publications emphasize our mission to turn complex theoretical ideas into practical real-world applications. So we started in July 2013 We have front end of wake-up board speech recognition system design on FPGA. In February 2014, we have wake-up board feature extraction on FPGA. In December 2014 or so, we have voice activity detector of wake-up board speech recognition system design on FPGA. In May 2021, we have reduced instruction set computer design on FPGA. In September 2022, we have University of Tripoli real-time density-based traffic light controller on FPGA. On September 2022, we have an alternative microprocessor bus structure design on FPGA. In November 2022, we have design and comparative analysis of an alternative approach of bus interconnect for system on programmable chip. In May 2023, we have design and implementation of smart traffic light system with Libyan license plate recognition on FPGA. On May 2023, we have design and implementation of 5 stages pipeline RISC CPU or RISC processor on FPGA. On May 2023, we have design and implementation of single precision floating point arithmetic logic unit for RISC processor on FPGA. On August 2023, we have an intelligent density-based traffic system with Libyan vehicle license plate recognition. In January 2024, we have development and comparative evaluation of innovative bus interconnect methodology for programmable chip-based systems. And finally, in December 2024, we have hardware design and implementation of automated rotary car parking system in FPGA. So now let's see what's the growing demand for FPGA engineers in the market today. So let's see the global demand for skilled FPGA engineers. First category, if we see the global FPGA market growth, it's a growth from 6.96 billion in 2020 to 14.7 billion in 2026. The key industries today for driving demand, we have in automotive, we have in telecom 5G, we have in AI and machine learning. Also, those is very active industry today for FPGA use. For the job listing, we have in LinkedIn and Indeed search, it have increased by from 20 to 30% annually every year. So from here, we can see FPGA design is becoming a core engineering discipline for students and researchers. Now is a great time to enter the field and contribute to its exciting future. Now in the hands-on session, let me introduce Engineer Nadia bin Salim to talk about her project titled High Performance FPGA Accelerated CNN for Character Recognition and Optimized Implementation using NICE2 software processor. Welcome, Engineer Nadia.
Thank you, Dr. Mohammed. Good afternoon, everyone. I'm Nadia bin Salim, a recent graduated from Computer Engineering Department at University of Tripoli. Today, I will take you through the hands-on session of this workshop, which is based on my graduation project. Our focus is on real-world case study and optimized implementation of convolutional neural network running on an FPGA using the NICE2 software processor. The system was designed for fast and accurate character recognition, and it demonstrates the powerful potential of combining deep learning with hardware acceleration. We will look at the system overview, CNN architecture, dataset, training, integration, and finally, the simulation and performance results. This slide gives a quick overview of the system we built. It's a high-speed CNN implemented on an FPGA platform using the NICE2 software processor. The setup allows for efficient task scheduling, real-time preprocessing, and better hardware resource usage. The system achieved an accuracy of 97.89% with performance up to 115 times faster than a CPU and 59 times faster than a GPU for the same task. These numbers clearly show the advantage of hardware acceleration for AI workloads. To understand our hands-on system, it's important to briefly review what a convolutional neural network is. CNNs are a class of deep learning models designed specifically for image-related tasks. Some of the most common applications of the CNNs include object detection, face recognition, and image segmentation. CNNs work by automatically extracting features from images using multiple layers of convolution, activation, and pooling. Their structure makes them ideal for recognizing visual patterns, whether that's handwritten digits, traffic signs, or facial features. On the right, you can see our architecture of CNN that was optimized and deployed on an FPGA platform for high-speed character recognition. It consists of 3 convolutional layers, each followed by pooling layer. Then there are 3 fully connected layers that are followed by the final output layer. For training the CNN model, we used the MNIST dataset, which is an extension of the MNIST dataset. MNIST contains thousands of labeled character images, including both uppercase and lowercase letters, as well as digits. The training process was carried out in Python using a typical supervised learning pipeline. We use the backpropagation algorithm for weight updates, combined with the Adam optimizer, which adapts the learning rate during training to improve conference speed. After training, the model parameters, including weights and biases, were exported for integration into the FPGA hardware implementation. Our system architecture uses the Nios2 soft-core processor developed by Intel. Nios2 is a flexible and lightweight processor that can be embedded directly into FPGA designs. Its key features include customizable architecture. You can tailor the instruction set and hardware components. Scalability, it can be optimized for size, speed, or functionality. Tight integration with FPGA logic, allowing communication between software and hardware blocks. This makes Nios2 ideal for managing system tasks such as pre-processing input data, controlling the CNN accelerator, and coordinating memory operations. In our design, the Nios2 processor acts as the control center for the entire system. Let's explore the hardware architecture behind our CNN system. The FPGA hosts both the Nios2 processor and the CNN accelerator. The CNN accelerator was implemented using System Verilog, with each layer of the neural network developed as an independent submodule. These submodules include convolutional layers, activation functions, pooling units, fully connected layers. All of these modules were then combined under a top-level module which interfaces with the processor. This modular architecture ensures parallel execution of CNN computations, reusable components, and easier debugging and simulation. It's a scalable system that could support larger CNNs in the future. In the final system, the CNN accelerator was added to the FPGA design as a custom intellectual property or IP block. A dedicated interface module was created to manage communication between the Nios2 soft-core processor and the CNN accelerator. This integration allows the processor to send input data to the accelerator to process the CNN computations, and also the final prediction results to be returned back to the processor. This type of hardware-software co-design ensures high performance and flexibility. The modular integration also makes it easy to upgrade the accelerator, adjust CNN layers, or extend the system with new features. This slide presents the simulation waveform results for the convolutional layer in our CNN hardware implementation. Before deploying to real hardware, it's important to simulate the logic and verify that every operation performed correctly. The waveform illustrates how the convolutional module processes input values through kernel filters, producing a valid output only when the computation window is fully populated. You can clearly observe the changes in control signals, clock timing, and output data as each convolutional cycle complete. These simulations confirm the correctness and timing accuracy of our design, which is essential for reliable FPGA deployment. This slide shows the simulation results for the final prediction stage of the CNN system. After completing all convolutional, pooling, and fully connected operations, the system produced a classification result. In the waveform, we can see the input data being fed into the output layer, activation and softmax operations occurring across clock cycles, and the final output prediction value being generated. The simulation proves that the system can correctly identify characters based on the trained CNN model. Again, simulation helps us ensure that the design is stable, synchronous, and error-free before it runs on the real FPGA hardware. This project was deployed on an Intel Altera FPGA development board, which includes the Cyclone FPGA chip and built-in support for Nios 2 softcore processors. The board provides I/O interfaces for sensors, displays, or communication ports, on-chip memory and logic elements, and support for hardware debugging and real-time testing. Using this board allowed us to test the full CNN system under realistic conditions, from input data capture to output classification. Let's now look at the key performance results of our FPGA accelerated CNN character recognition system. The CNN model achieved an accuracy of 97.89%, which is very high for a lightweight character classification network. But more impressively, the FPGA implementation resulted in a 115 speedup compared to running the model on a standard CPU, and a 59 speedup compared to running it on GPU. This highlights the efficiency and parallelism of the hardware implementation, making it ideal for real-time embedded AI applications. In conclusion, we demonstrate significant improvements in speed and resource utilization over traditional CPU-based solutions. The new architecture allows efficient task scheduling, real-time data preprocessing, and smooth communication with the FPGA-based CNN accelerator, which is closing an important gap in the current character recognition solutions. To conclude the results section, here is a short demo video of the CNN character recognition system running in real time on the FPGA. The characters shown in the video are handwritten. The input image is processed directly by the FPGA-based CNN, which detects and classifies each character accurately. This video confirms the system's practical performance, combining both high accuracy and fast execution on hardware, with real-time results powered by the custom-designed FPGA logic and Nios 2 coordination. Now we can.
Okay, did you finish?
Yeah, it's finished. Go back to Dr. Mohammed.
Thank you, Engineer. Finish, and then we'll go to the next slide. So in the end of the workshop, we thank you for your attention. If you have any questions or would like to explore cooperation or wish to learn more about our FPGA projects and research, please feel free to reach out. You can visit our research group on University of Tripoli website, this research group, or email me directly through this email. This is my email, or you can call me through my cell phone number. We are always open to knowledge sharing joint projects about FPGA embedded systems and AI. Thank you for your attention again, and have a great day. If you have any questions, we are waiting for questions. Thank you, Dr. Ali. Thank you, everybody, for your time.
Thank you so much, Dr. Mohammed, for this very important workshop. Actually, I've enjoyed it.
Yeah.
I hope, inshallah, all will already benefit from it. This is University of Tripoli. Apart from it.